I'm excited to be here. Today my talk is entitled Celerity, an open source 511-core RISC-V tiered accelerator fabric. And my collaborators in this work are University of Michigan, UC San Diego, my university, University of Washington, and Cornell. So in my talk, I'm going to have three parts. The first is talking about the 16 nanometer TSMC chip that we designed, which has 511 RISC-V cores. The second part is focusing on one of the subsystems of that SoC, which is a many-core design, which you can, all of this code that I'm talking about today, everything you see, the cores, the ASICs, the printed circuit boards, the BGA substrates, the FPGA firmware, you can download it all. You don't have to design a single thing in order to recreate what we did here. Okay, so, and the top level link is Open Celerity, and then there's these sublinks. One is this many-core I'm going to talk about, which is the closest thing we have today to an open source GPU that's available for kind of throughput, high efficiency, high energy efficiency processing. And then I'm going to also talk about BaseJump, which is a kind of DNA for open source ASICs that we've been developing in my group over the years. And that includes the designs for the printed circuit boards, the BGA substrates, the high-speed interface to the ASIC, and also a library of components like the standard template library for C, but for system Verilog that allows you to rapidly construct systems. So the SoC, as I mentioned, is a collaboration with Michigan, San Diego, and Cornell. There are about 20 graduate students working on this project, and 5 professors driving the design of the SoC. We completed it in 9 months. So, of course, in order to hit 9 months, we had to leverage a lot of stuff that already existed, and of course the RISC-V ecosystem was very central in this. We were able to leverage the software toolchain, we were able to leverage the architecture, the ISA, microarchitectural components from Berkeley and Sci-5 like TileLink, physical design, leveraging the experience of other RISC-V implementers and finding out what tricks they use to get the infrastructure working. And then, of course, the test suites that are out there, and then the FPGA gateware that has been generated. So the chip that we designed is what we call a tiered accelerator fabric. The name of the chip is Celerity. Celerity means with swiftness. And since we had to get this chip out the door real fast, it seemed like a really appropriate name. And this idea of a tiered accelerator fabric essentially has 3 key components. There's a general purpose tier, which is going to run Linux and do your control-intensive code. Then there's going to be a many-core tier, which is for the throughput processing, high energy efficiency, high density. And then there's going to be a specialization tier, which is really like the secret sauce for your SoC, where you're going to put your hard-coded fixed-function accelerators. And all of these tiers are interlinked with high-speed parallel connections. Okay. So the chip, as I mentioned, was implemented TSMC 16 nanometer FFC. It's 25 millimeters die area, 385 million transistors. And then the 511 RISC-V cores, that's kind of a funny number. Did one of the cores not work? Did you not figure out the power of 2 thing that we're all into? Well, the reason is there's 5 Linux-capable cores, which we got from Berkeley, the Berkeley Rocket cores. Then we have a many-core array, 496 cores. That is like an even square. And then we had another 10 cores thrown in there for doing very low voltage operation, and there's an on-chip LDO that powers that array. And we use exactly the same source space for the 496 core array. As the 10 core array, we just had to change 3 parameters at the top level. In addition to this, on there is this binarized neural network. So a binarized neural network is a special kind of neural network that uses binary weights. So that allows you to reduce the amount of memory that you need to store the neural net, and you have a relatively low drop in accuracy for doing this. So this is a kind of a hot topic of research. The design had 400 megahertz I/O, and that's just using off-the-shelf single-ended CMOS I/Os from the fab. The Rocket Core and Accelerator ran at 625 megahertz, and then the many-core array ran over 1 gigahertz. And we used a flip chip package. Okay. So I'm going to talk about these 3 components a little more. So the general purpose tier is responsible for running Linux and doing, kind of control-intensive codes or, your TCP/IP stack or spec-like programs. We leverage the RISC-V Rocket cores. And then we also leveraged a bunch of components from the BaseJump suite that we've been developing in my group, which includes the high-speed interface that goes off-chip to an FPGA, which provides things like DRAM and PCIe and so forth, and then also our open-source motherboard designs. Okay, so the Rocket cores, we've seen a lot of them. They're really nice design, very flexible. We pretty much use the kind of the off-the-shelf settings for the core and try to kind of follow in the footsteps of other people in terms of what they've taped out. And we found it very nice. It's really hard to find a Linux-capable core out there that's open source, right? So in terms of communicating off-chip, we had this BaseJump library, which provides the front-side bus, and then we also have open source package and then a bunch of code for testing. Okay, so here we really found the RISC-V ecosystem to help accelerate our schedule. It was very effective. The Rocket cores, but also a lot of the components that we'd built up in the BaseJump library really helped. So now I'm going to talk about the Manycore. And so I think a lot of us are pretty comfortable with the idea that there's going to be RISC-V, open source RISC-V, Linux-capable cores. I think maybe the next step is to start thinking about the other parts of the system. For instance, what are we going to use for high-throughput compute on our SoCs? And so BaseJump Manycore is my group's attempt at an initial answer to this question. The code is available. We're excited to have people try it out. So let me tell you a little bit about that. So in our design, we put down 496 cores. And actually, the way we did it is we originally were going to have 32. And then we realized that the core was actually about 10 times as dense as we thought it was going to be. So then we went up to 300. And then about 2 days before tape out, we realized we had another like 5 square millimeters of die area, so we just increased it to 496. So we have very rapid iteration time that we were able to achieve. And in fact, if you were to fill a full reticle die, you could get over 35,000 cores on a single piece of silicon. Okay, so these cores, we used a RV32IM RISC-V implementation. It's also available online. It's a very well-designed but basic implementation of a RISC-V pipeline with scratch pads. But the secret sauce is really how we connect these cores together. So some of you may know I've spent a lot of my life designing many cores, including the MIT RAW processor back in the late 90s. And this network is way better than anything we designed back then. And basically, the model for this Manycore is that any core can do a store instruction, and based on the address, it will get routed to a particular other core. So there's basically all of the SRAM on the chip is mapped into an address space, and that address is translated into an XY coordinate on this mesh. And so then each packet on the mesh is just an 80-bit flit that includes the source and destination, and then usually an address and some data. Okay? And then there's a very efficient way of implementing fences where there's the source address is routed back to the source, indicating that the store has completed. Okay? So, and the routers are absolutely tiny. We don't use virtual channels. They provide in-order delivery. They're deadlock-free. And we have the absolute minimum buffering you need in the system to keep the area down. So if we pop up a level and think about how this Manycore is integrated with the rest of the system, we use all of these parallel links on the left. There's the Rocket cores. And the Rocket cores, they have the ROCC interface. So we use, for each Rocket core, it has its own ROCC interface that connects to one of the routers in that mesh of the Manycore. And then on the other side, we have a whole bunch of parallel links that go from the Manycore to the neural network. And so the Rocket core can issue an accelerator instruction, which will allow it to do stores into any of those cores in the Manycore. And the Manycore can do a store instruction to store into any memory in the Manycore, or it can store off the side of the edge of the chip into the state of the accelerator. Okay? Okay, so this remote store programming model is very powerful, and one of the things that it enables is very efficient producer-consumer programming models. So we can have a kernel on our Manycore. Maybe there's a bunch of cores that are doing FFT and then another bunch of cores that are doing another kernel, and the FFT can, just by doing stores, transfer its data as it's computing it to other cores to compute on. And the key challenge here is how you do synchronization. You know, how do we know that the downstream kernel from the FFT knows that the data is available? And the way we do this is we leverage the common primitive load reserved that's in the RISC-V architecture, but we add another instruction. And the instruction, instead of trying to enforce mutual exclusion, it's actually enforcing synchronization. And the way it works is it actually waits for the reservation to be broken, and then it knows that the other core has transmitted the data. Okay, so it's a very efficient mechanism for synchronization. You know, we have some hopes maybe one day this will be integrated into the RISC-V ISA. Okay. We're also interested in a fast path for getting CUDA working on this Manycore. The model is not exactly the same. Our model is a much more embedded-friendly model. Our goal is not to just slosh things back and forth out of external GDDR5 RAM. The idea is to leverage the locality that's inside the chip between the cores and have a programming model that exposes that. Okay, so if you're interested in programming models for Manycore, we're happy to facilitate you developing on our architecture, for instance, by providing images on Amazon F1 that you can program with. Okay, so these cores, as I mentioned, are very area efficient. So you can actually fit 42 cores per millimeter. In an earlier slide, I mentioned I think Rocket is about 5 cores per millimeter in this process. So that's a nice complement in terms of getting general purposeness and also getting high compute density. And we have some comparison to other things, other open source projects on the right there, and we pretty much blow away everything in terms of density. Okay, so how did we build this Manycore tier? Well, one of the things we leverage very heavily, something about like 80% of the modules in the Manycore are from this BaseJump STL library that contains all these components, and I'll show you what some of these are. We, of course, used all the open source testing infrastructure for the RISC-V ecosystem. And then in terms of the back end, we basically hardened each kind of core and then replicated across the die. So we have a hardened one tile for the Manycore, we've hardened one Rocket core, and we hardened one BNN implementation. And on the right there, I show kind of the die outline and then their relative sizes on that die. Okay. So this is a breakdown of the Manycore tile. And if you look at the pie chart, you'll see that over 2/3 of it is just memory. So this is very, very efficient in terms of the overhead of the combinational logic. And we use single-ported memories for DMEM and IMEM for area efficiency. Okay. So let me talk about the specialization tier very briefly. RISC-V has not yet defined a standard for neural networks, I think, but maybe it's coming. We'll see. So I won't spend too much time on this, but basically, we wanted to implement this neural network as a kind of secret sauce for our SoC, and we wanted to do it very rapidly, and I'll tell you a little bit how we did that. But one of the key challenges with the neural network is the weights. Okay? And so we wanted to have a clever way to store the weights without going off chip. And so there are two things we did to do this. The first is we used that binarized neural network design, which uses binary values for the weights. And then the other thing we did is we said, hey, in this Manycore, we have a lot of memory. So rather than baking that memory into our neural network accelerator, we're just going to leverage all the memory in the Manycore. Okay? So, and so what we did is we just had a little program that ran on the Manycore, and each tile would just iterate through a local array of memory and then do stores to the addresses that are owned by the neural net accelerator. And then you see the little red square, which turned into green squares. So all those tiles are just sequencing through the contents of their memory and streaming it to the neural net accelerator. So this way, we can just leverage the SRAM in the Manycore. And then when we're not doing the neural network, we can do things like video decode on the Manycore. Okay. So by combining the general purpose tier, which gives us the kind of nice glue properties for the SoC, with the Manycore and the Specialization tier, we can get about 400x improvement in performance and power. Okay, so to generate this accelerator, we used HLS, high-level synthesis, and for generating algorithmic accelerators, this is a really nice way to crank out hardware fast. Okay, so all of the code for this chip is available at opencelerity.org. Now I'm going to talk about BaseJump. So BaseJump, is part of all of the IP that we leverage to build a system quickly. And I'm going to go through some of the components here. So in my group, we really just love building hardware, and we kind of think of it as a sport, like cranking out chips. It's suffering, just like, doing a cross-country run. But at the end, it's very rewarding. And so we've been sort of building up this ecosystem of hardware. And I like to call it the DNA for open source ASICs, because the thing I realize is the more ASICs you build, the easier it gets, because, well, you just take the stuff you did last time, and it's like, oh, what should my power grid looks like? I'll use the same design I did before. What should I use for general purpose compute? What should I use for I/O? Over time, you build up all of these techniques, and they'll just become the new defaults for your chips. And so you can think about, at each company, there's a kind of DNA that's going through all their chips, even when the chips are, unrelated products. And so rather than us evolving our DNA all individually, there's the idea that, we should be evolving this base class of DNA for the whole world as a joint ecosystem. Okay? So here are the components of BaseJump. So we have BaseJump STL, which is all of these reusable components like asynchronous FIFOs, routers, network on chips. Then we have BaseJump socket, which is a socket definition for an ASIC. So the idea is just like the old Intel motherboards, you have the 1151 pin socket, then the corresponding Intel processor will fit in that socket. It's a similar concept for open source hardware. Okay? Then we have motherboards, which accommodate those socket interfaces. And then we have two flavors of motherboards. So one flavor is an emulation motherboard. So there's an FPGA where your ASIC would go. And then in the other flavor of motherboard, that's where you stick your ASIC. And then we have the Manycore, which I mentioned, a bunch of glue code and adapters for doing cool stuff with Rocket. And then a high-speed FPGA bridge, which allows you to avoid NRE by scavenging expensive IP cores from an FPGA rather than licensing those PHYs yourself for your chip. Okay? So as I mentioned, BaseJump STL is like C++ STL, but for system Verilog. So we have all these blocks. And I think on the next slide, here, this is a list. This is not a list of modules. This is a list of directories that each contain 20 modules or so. So there's about several hundred modules, things like network on chips, configuration chains, asynchronous FIFOs, priority encoders, pretty much all of like the conceptual hardware blocks that you could think of for designing a chip. And all the testing code that goes with it, more importantly. So let me talk about BaseJump socket. So this is how BaseJump socket works. We give you a pad ring. The pad ring defines a basic NOC interface. You have, data bits going out, a valid bit, and some credit signals coming back in. And then you use our RTL code for doing a really high-speed implementation of that goes off chip. It's DDR, so we're synchronous. And then we have RTL code that for FPGAs that uses the crazy FPGA SerDes and the delay elements, all that. So you just use that code off the shelf. And so you're really just thinking about designing the RTL for the inside of your chip, and you don't have to think about building out, what is my motherboard going to look like? What is my package going to look like? What is my I/O interface going to look like? You're going to just take that off the shelf from us. And then we have BGA substates that we design. You can see there in the middle. These are designed to accommodate different sizes of chips. The design for the substrate is available off our website. We can give you the address of the company to email, and they will manufacture 100 of them or 100,000 of them for you. Okay. And then finally, we also have a socket, a true socket, where you can take your test chips and insert it in the socket. So you have two choices. You can either just solder your chip onto the board, which you do for production, but then you also have the choice of using the socket, so you can test a variety of your ASICs. And you can build a couple of boards and then design 10 different ASICs and then just try them all out with the same boards. Okay, so then here's the boards. Okay, so we have two boards. There's double treble, which is on the left. that has an FPGA, so you can emulate your design before you tape it out. And on the right, it's the same board design, but instead of the FPGA, you have the socket to put your ASIC in. Again, all of this stuff, you can just, we have the designs online, you can just order the components and have it assembled. Okay, so I'm gonna wrap up and just show you the BaseJump flow here. So use BaseJump STL as a way of raising the level of design, hardware design. Instead of designing all of your own leaf level components, we can leverage that infrastructure by crowdsourcing across the world people's collective knowledge and how to build those components in a bug-free way. Then you use the patterning definition that I described, so you can just glue your RTL in there. And then you can emulate using the board design that we have put online, which includes the FPGA firmware. And then you tape out your chip. You assemble it with the open source package. And then you can stick that in the socket there in the motherboard. Now you pretty much have gone from the RTL for your SoC to a functioning system without having to actually do any of the hard work. Okay, so those are the 3 parts of my talk. And I'm going to wrap up now. All the code for what I described, including the actual hardware, the PCBs, and the SoC chip that we taped out, it's all available online. Feel free to check it out. And I'd like to, of course, thank all the collaborators involved in this project. Happy to take some questions. Okay. So the question was, what about clock domains? What about DC-DC converters? Did I miss anything else? Oh, and how many? Okay, yeah. So we have a separate clock domain for doing off-chip I/O. We have a clock domain for the Manycore, and then we have another clock domain for everything else. And then for each clock domain, we have a PLL. The PLL is actually also open source. It's actually all digital implementation using standard cells. Okay? It was designed by a faculty member at UCSD, Ian Galton. In terms of in other chips that we've designed, we've actually just used the on-chip clock generator, which is just a tunable ring oscillator, and that actually is a very effective way of not having to pay for a PLL for your chip. You lose a little bit in the parameters, maybe you'll lose 5% in jitter or something like that, but maybe that 5% doesn't matter that much to you. And then the DC-DC converter is a similar thing that also was a in-house design that was, except for a capacitor cell that also is all standard cells. So so the question was, how much does it cost as an academic to do all the board designs? Well, you don't have to, wait, do you want to design the boards or you just want to use our boards? Oh, a board, the bill of materials for a board is like $350. If you want to assemble 20 boards, it'll cost you maybe $200 per board for the assembly costs. Obviously, the big ticket item would be the silicon, but you can do MPW runs to get the cost down there. Yeah, so we actually designed the boards to be very inexpensive. We don't use like high-end Xilinx Vertex parts for our boards. We use Spartans to keep the cost down. Great, thanks a lot.